Our next speaker, David Bordenave, we'll be talking about polarimetry. We've already heard some discussions about polarimetry in the context of the Dapper concept. You'll be telling us about the cosmic twilight polarimeter. David? And you're still on mute if you're talking.
Oh, can you hear me now?
Yes, very good.
Okay, I'll maximize it again. Okay, great, thank you. So as was mentioned before, a lot of this has been built up by Jack Burns and David Orpetti and Joshua Hibbard just recently. And I'll be going over essentially some of our recent experimental results with the cosmic twilight polarimeter, which is essentially our ever-evolving test bed for a lot of the technology and the techniques used by the Dapper small sat mission, and essentially testing out a lot of the methods that were presented, especially for David and Joshua's talk, of using polarimetry for 21 centimeter cosmology, especially around the moon. So I'll kind of jump right in, skipping a lot of the science which was brought up earlier, and kind of going over one of the key observational methods that we're using. And that is essentially using the polarization information from a instrument. In this case, we have a cross dipole, and we're able to, we're essentially using the non-ideal behavior that is normally calibrated out for conventional radio astronomy. And we're using that to gain back some extra information that would otherwise be lost. And most conventional experiments don't actually consider or can't consider because they're using single dipoles. So they're not actually sensitive to the full polarization. And this kind of is shown by this matrix of maps that we have on the right-hand side. So this is essentially the transform of an optical system, in this case, our cross dipole. And it is essentially showing how an incoming Stokes vector, so the polarized and unpolarized light from the sky or any source, incident on the antenna, is then modified, or this is how it's observed by the instrument, and it's then giving you then the net observed polarization vector. So we can see that for the most case it's pretty obvious. So there's Stokes I to what the observed Stokes I is, and then down the diagonal this is Q, U, and V Stokes. So this is the linear polarization in the middle, and then circular polarization. And for the most part, the power is maximized along the diagonal and this little inner square, which is kind of the main polarized sensitivity of the instrument. However, the really peculiar part is these maps on the off diagonal, and these are kind of what's referred to as polarization leakage, which is essentially the exchange of polarized and unpolarized light that is not really ideal in most cases, but for this case, it actually gives us back some extra information that we might not otherwise have. And that's based on the spatial structure in the field of view of the antenna. So the middle of these maps is actually this pointing, like the main pointing. And we can see that the polarization leakage, it's actually maximized away from the center of the beam. So off bore site sources will illuminate these patterns, and depending on how much structure there is or how anisotropic the sky is, you will then be able to generate essentially a net polarization that can even exist without having any intrinsic polarization from the sources themselves. So for the moment, we'll only be really considering the first column, and since we don't really have any reliable polarization maps, so if we just assume that the sky is just 100% unpolarized, I can show you a little example in the next slide. So I want to kind of briefly mention again, so this column is essentially the beam weighted foreground for the first column using the Haslam 408 megahertz map. And you can see again, so Stokes I up here, there's kind of a big lobe. Stokes Q, U, and V, as measured by the instrument, have these quadrupolar fields. So, and quadrupolar fields, and then there's an octopolar field for the circular polarization. And as I essentially move the antenna through the field of view of the, or through the sky by the Earth, or from the Earth, we can essentially see that as the time evolves, it is sweeping through the sky and presenting a different view and a different set of correlated structure that essentially repeats every LST day. Or for a satellite, for instance, it would then repeat whatever rotation period or orbital periods. So we were essentially able to modulate the structure of the sky, which is then correlated in what these polarized waveforms are. And this is essentially kind of the basis of what David was talking about using, or David and Joshua, about having many of these models and of the beams, of the foregrounds, of the spectral indices and everything. We can make these representative waveforms, which will then describe roughly, the eigenstates of the system itself, like the entire antenna sky environment system. And I'll kind of go on to then, how do we actually observe this? So this is then the cosmic twilight polarimeter, or kind of the most recent rendition of it. We're actually reusing part of the paper array, dipole, and some of the hardware. So it's essentially just one array, one element of the array that we had laying around. And here's just a quick system overview. It's a very crude system, all considered, because we were using essentially equipment that we had on hand. So it wasn't necessarily ideal for the exact science, but it was very, it was sufficient enough to actually do the experiment at a higher frequency, so we're not as influenced by noise. And it was vetted from the development of the paper array. So it's just a cross dipole, gain stage, bandpass filter, and then we use an off-the-shelf software-defined radio. We measure the temperatures of the active components. That's important for the calibration. And then we just had a spectrograph and a correlator to get the polarimetry from the data. Just some quick pictures of the lab measurements. We didn't have any active calibrations on the instrument, which is one of the drawbacks of using non-purpose-built hardware. But we ended up essentially characterizing the active, the RF, the receiver board, and the balun as a function of temperature in this temperature-controlled box with a VNA. And we were able then to generate essentially an instrument model given what we know of the environment that the instrument is in, which is being modulated.
David, 2-minute warning.
And just here's the deployment. Here's some of the calibration and pipeline. We ended up using essentially the gain models and spectrokurtosis to get rid of RFI to get their output. And then here's a quick snapshot of the raw data, which is just showing off some of the problems of RFIs kind of abound everywhere, both out of band and in band. However, one of the key aspects I want to get to is this is kind of essentially the main result that we were able to get. The colored blue and orange line are essentially two different configurations of the instrument. And then the dashed and dotted lines are the two models that correspond to them respectively. And what we essentially did was rotate the antenna 20 degrees in azimuth to change, essentially like perturb the system. And what we observe is that overall, Stokes I looks very close to what we'd expect. Stokes Q is kind of, there's instrumental effects I think that are at play here, or environmental, like scattering, that's adding extra polarized emission. But U and Q, U and V Stokes are actually very, very good in that they're very low noise for 2 weeks of observations that were averaged for each of these. And they do happen to follow the predictions of the simulation. So these are essentially the dashed and the dotted are the models that we'll be using in the system, in the extraction pipeline. And they actually do happen to follow what we'd expect. And here's a long-term experiment. So this is essentially the last configuration we had the system in, and it was running for 90 days. and then showing very, very good stability. So these curves are very reliably, they're essentially throughout many different environmental changes or weather or any sort of perturbations, really. So this kind of shows that's very much an astrophysically related signal. And I'll leave it at this. So essentially, the experiment more or less shows that the technique of using induced polarization works. However, there's still some deficiencies with the instrument that we'll be addressing within future version. And this kind of then also goes back to Dapper in that a lot of these problems can be fixed by going to the moon. Essentially what Joshua was mentioning, like the interference and the ionosphere, those won't be an issue anymore at the far side where it's shielded. And it will also mitigate some of the environmental problems where we're not as subject to scattering or ground effects on the antenna as well. So having a free-floating antenna and being isolated will actually benefit the instrument as well. So Dapper is kind of the eventual progression of the system, but the CTP is essentially the ground-based pathfinder for this development. And yes, that's pretty much it.
Great, thanks, David. Unfortunately, we don't, I think, have much time for questions, but maybe you could answer them in the chat if there are any. So
sure.
Thanks, and let's move on to the next speaker.